In the 2028 timeframe, we start to introduce the light sync technology, which is based off of diamond color centers. That allows the ability to communicate between chips through coupling of the qubits to connect these systems together.
IonQ is poised to redefine the quantum computing landscape, projecting a staggering 80,000 logical qubits by 2030, potentially unlocking the power to crack encryption. NIST has us on a timeline to upgrade to PQC by 2035, so this 5-year gap may spell doom for cybersecurity. Of course, these machines will also revolutionize industries from finance to drug discovery to AI. How is IonQ boosting their roadmap by orders of magnitude? Learn about their cutting-edge acquisitions and bold vision for scalable, error-corrected systems in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the Senior Vice President of Engineering and Technology at IonQ, Dean Kassmann. Welcome to the show.
It's a pleasure to be here. I look forward to talking today.
Yeah, it's been a little while, a couple of years since we've had IonQ on. We had Chris Monroe on. That was a pretty great episode. And at the time, I guess when I was thinking about the IonQ roadmap, if I extrapolated, I wouldn't have predicted the exciting news that came out recently. So, we will start with the excitement, I think, if that's okay. I'm sure people listening want to know how all of a sudden you guys are going to be orders of magnitude ahead of the rest of the world when it comes to logical qubits.
Yeah, it is exciting, and it represents a lot of the focus that we've had and keeping abreast of what others are doing, and honestly using our capitalization and I would say, the business acumen of our leadership team and our CEO to its fullest extent, right? So let's kind of rewind for just a moment. And so the announcement you're talking about with our roadmap, right? Earlier this year, actually just a little over 5 weeks ago, kind of the beginning of June, we announced an updated roadmap, updated computing roadmap that leverages our recent acquisitions of both LightSync Technologies as well as our planned and announced acquisition of Oxford Ionics. Our overall computing roadmap remains based off of trapped ions. We still believe in the core capabilities that trapped ions bring to the table in terms of their native gate fidelities, their ability to produce high quality gates and scale. And so as we've been going through our technology development over time, the focus has been on driving performance, driving scale, and driving enterprise-grade capabilities into our engineering, into our physics and development processes, our R&D, and the acquisitions that were part of the building blocks for kind of announcing that new roadmap leverage our existing thinking and philosophy along those axes. And so let me pause there, but I'm happy to jump into our LightSync work as well as the Oxford Ionics technology stack and how they help us.
Yeah, so to set the stage, one thing I've been talking about on the show pretty much from the beginning is that I believe the path to scale is not one big box with a whole lot of qubits in it, but instead a bunch of little boxes that are somehow perfect. Like, depending on the modality, we're going to figure out what that perfect number of logical qubits is. It could be high, it could be small, whatever it is. And then you take those boxes and you daisy chain, or however you want to multiplex and think about it that way. And then you end up with one bigger box, right? Because qubits don't care where they are, I guess, in theory, if you really think of them as pure entities. So you guys landed with these acquisitions on a 256 to 12 ratio, right? So the idea is that we have 256 physical qubits, and that becomes 12 logical. And they become more perfect, actually, if I'm reading the roadmap right. They go from errors into the 10 to negative 7 to 10 to negative 12, I believe. So it's a great jump there. Interestingly, IBM came up with the same number. They came up with this idea of 12 logical qubits in one of their little modules. I thought that was kind of funny. I'm sure you guys just did that independently, but I thought that was kind of a funny number to end up on. That'll be like the new scaling thing that we think of when we think of like how RAM goes up or whatever. It'll be 12 more. So I guess let's talk about the technologies in those acquisitions that enabled each of those factors. Creating that perfect box, that little tiny box, and then making those little boxes talk to each other. I mean, just to keep it super simple.
Perfect. So the basic building block is the ion trap.
Hmm.
The Oxford technology, we've already demonstrated 3 nines of fidelity in the IonQ systems in our ion traps. Oxford Ionics has demonstrated 4 nines of fidelity using their electronic gates. They currently hold the world record actually in 1 qubit and 2 qubit gate performance. And so building that perfect box is all about getting a large number of high quality qubits. And the Oxford technology is what allows us to change the gate technology from laser based gates to electronic based gates. The laser based gates have been doing very well to date. The recent work over the last 2 years in the electronic based gates has seen maturation and continued performance increases and an ability to leverage existing semiconductor processing techniques. And so the fundamental way those gates work is with an RF antenna embedded into the ion trap that generates an oscillating magnetic field that interacts with the dipole of these trapped ions to actually affect the qubit transition. Because it is a mechanical or not mechanical, because it's an electronic gate and it is a semiconductor based manufacturing technique, it is inherently more scalable than the optical engineering laser based approach. And so we've been in kind of a watch and monitor mode for a while in terms of the technology. And so moving to that gate technology allows you to increase the density of the number of qubits you can put in a single box or a single trap.
Hmm.
And it's not just a 1D type of arrangement where you see in kind of IonQ's historical past. You now have an ability to move to a 2D kind of topology and leverage a kind of tiling of semiconductor dies to just increase that scale, but maintain 4 nines of fidelity as you scale those number of qubits. Optical or single long chains of ions, as the chain length gets larger, you have to manage the various error sources that kind of start to creep in with long chains. And so that's where you start breaking the long chain into multiple chains and relying on shuttling and ion transport to maintain, I would say, high quality, high fidelity chains in that overall architecture. And that architecture will scale. If you look at the overall unit economics, the part of the rationale for the thesis behind moving to the electronic gates is the, if you will, cost per qubit, right? You have an ability to leverage and even bring down the overall unit economics even more so than with laser-based systems, with these electronic-based systems, so that you can build that perfect unit box of items or unit box of qubits
Hmm.
and really kind of push the limits. And the limits there really start getting into just how you can operate these kind of 2D arrays, at scale.
So when people visualize it, it's sort of like a little rectangular cartridge almost if you look at it on an illustration. And in there you've got your 256 ions and they become, like we said, 12. So the goal is in 2026 to have one of these actual cartridges, if you want to call it that, working, right? Like
Absolutely.
so next year we'll have 256 and the 12 logical as a working thing. But then in 2027, you're connecting enough of these together that we have 800 logical qubits. So all of a sudden in 2027, we're talking pretty rampant advantage, I would think. I mean, in use cases, you can't even get close to anything like that power-wise. So now we have to really talk about how do we go from one of those to many of those and how confident we are that that works.
If you think about what's allowing the 256 to 10,000 jump,
Hmm.
that is a continued investment in the actual trap itself, the manufacturing techniques to increase kind of die sizes that you would expect in kind of standard semiconductor techniques. And so you have the ability just take any analogy that you have in classical semiconductor world where you're trying to start with a small building block, but you then have the ability to simply replicate that.
Hmm.
And so if you think about, a 256 qubit system, or let's just take a 64 qubit system, an 8 by 8, right? 8 by 8 square. You can then scale to 256 and scale to, a 100 by 100. All of a sudden, you now have a 10,000 qubit system. And that's purely by scaling that side length associated with the dies that you're pushing through the semiconductor process with the same fundamental building blocks. Then, as you said, you start to connect these together. Now, in the 2028 timeframe, we start to introduce the light sync technology, which is based off of silicon vacancy color centers, right? Diamond color centers. And that allows the ability to communicate between chips through, edge coupling and other coupling of the qubits to be able to connect these systems together.
Okay, so to clarify, the connecting won't happen until the jump from 10,000 physical to 20,000 physical.
That is correct. That's
Or,
the current roadmap
yeah.
assumes that at in around the 2028 timeframe, we have moved the integration work forward to a point where we have the ability to couple these individual dies together photonically or optically to be able to drive that entanglement with multiple channels of communication between the different QPUs.
Okay. And then it's in 2029 that you're going to then do that 20 times, let's say, and end up with 8,000 logical qubits. But somehow in that time frame, it's estimated that as I mentioned earlier, that the error correction gets even better. The logical error rate, I should say, gets better. What would be causing that change if we're just cutting and pasting?
So what you have in all of these cases is as you start to go from 2028 to 2030, you have incremental improvements both in once again, the trap scaling itself,
Mhm.
plus the number of QPUs that you can then scale together. So the roadmap from kind of 3 years off to the end of the decade represent simultaneous scaling of both the number of interconnects as well as the size of those QPUs. Across any of those topologies, you have the ability, based off of the connectivity we have, to apply different error correction techniques. And the overall work that we have is those numbers that we have for our qubit counts represent early analysis for deep as well as shallow memories based off of the most recent error correcting techniques that are out in the literature for LPDC codes, the low density parity check codes that are optimized for generally these trapped ion systems or these type of loose connectivity systems.
And I mean, in theory, there could be some breakthrough in error correction that even improves this. Right?
Absolutely, right? The
Yeah.
the beauty of the architecture is error correction is once you have the hardware fundamentals or the primitives in place, the error correction is a layer that sits on top of that. As new error correcting codes come out, we have the ability to optimize and then add them to the hardware stack.
Yeah, that's super exciting. But when I look at that roadmap, the first thing that came to mind for me, with my background especially, is I was looking at the 2029 to 2030 timeframe, and I had to point out something immediately. And I said it's my words, not IonQ's, but immediately I had to put on X that my exact words were IonQ has a new roadmap for quantum computing that, frankly, has them cracking encryption this decade. My words, not theirs. That's what happened to me. And it's true, in my opinion. I mean, because we've got 200,000 physical in 2029 and 8,000. And then as you tip into 2030, that's 2 million physical and 80,000 logical. And basically read any paper you want, Regev, whatever. You read any of them, and that's that's the point. That's the inflection point, somewhere in there, somewhere 2029, 2030. Have you guys been kind of losing sleep over that, or or like having conversations with three-letter agencies? Like, I just got to wonder what goes on when you realize, whoa, we're putting out into the world that the 2035 timeline, which NIST has set up for post-quantum cryptography, will not apply if this is going to come to pass. So I'd love to hear your thoughts on that. I mean, it's a big question, I guess, but
It's a big question. It
yeah.
it is definitely on our radar. It is an active area of internal conversation. It's a area of conversation that we're having with, I would say, those three-letter agencies.
Hmm.
It is a, I would say, a capability that we do take very seriously in terms of like the being good stewards, if you will. And so in this, you can think about it from many different angles, but IonQ is definitely pushing the limit there. It is the time frame that we're looking at that occurring. If you look at DARPA's QBI program, right there, and the use cases that they have there, if you look at, like you said, the other sources, it's around those, logical qubit counts, those overall physical qubit counts and overall performance that you expect to see these things start to happen. And so that speaks to not only, our computational capabilities, but it also speaks to the the networking aspects, right? The security aspects, the cybersecurity aspects that like IonQ has been investing in for some time now. And so we have actively been growing and expanding our overall networking footprint and our overall networking ambitions in terms of the security aspects and the capabilities over the last, I would say, 3 years. And that's, partly, showcased with some of the recent acquisitions with IDQ, right? The acquisitions of Capella, right? We just announced today, the closing of the Capella acquisition with regards to being able to demonstrate QKD in space from a secure perspective.
Hmm.
And so the overall security, both in terms of, some people refer to it as both the safe cracking and the safe keeping, right? Like we're basically looking at driving both capabilities forward, right? On the computational side for breaking encryption, but also being able to make sure it is done in a thoughtful way, as well as investing on the safekeeping aspect as well.
If you think of like next year as a, or maybe the year after 2027, as sort of like a chat GPT moment, because you'll have this like serious advantage in the machine itself. You could think of the cracking encryption thing as more of like a AGI moment, like something that we're all really a little nervous about, and what safekeeping and everything will be required. So I would love to poke on this just a little bit. I'm curious. A lot of companies are starting to pull their most powerful resources or all their resources sort of off the public clouds, right? Like we've seen this. Like originally D-Wave had machines available, however, then they were like, oh, but if you want hybrid, you can only do it through our Leap environment. And then now they're like, no, 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 you can only do everything through our Leap environment. How do you view your machines being accessed both in the short term and by the time this level of power is achieved? Because I do have a follow-up question you might be able to predict.
We continue to invest in our cloud platforms. We're still
Mhm.
the only provider that is actually available on all of the three major cloud platforms, right? And so we were the first to do it, and we're still the only to be able to be available. And so we're continuing to invest in that, in the rich APIs, the hybrid APIs, session capabilities, all of those things as we move forward. And so over time, from a business perspective, we want to make those APIs available to scientists, to engineers, to developers to be able to, create things that we never even thought possible. But you can imagine that, it's silly, but with great power comes great
Yeah,
responsibility as well, right? And that really
truly.
comes down to making sure that as we're providing and creating machines that are absolutely unique in their performance and capabilities, that we are good stewards of how they're used. And so it's definitely, something that the management team talks about, something that we think about from our overall strategy. And so it's and definitely an ongoing internal conversation.
Okay, because right now, by 2029, Bitcoin's dead unless they do something. And by 2030, all other encryption that's vulnerable is now on the table. Do you anticipate making some kind of changes to the stack and where you can be sort of big brother in a way to prevent use of this machine in that attack so it becomes just a nation state kind of approach that we all know will happen? If you could just talk our listeners through a little bit of what you could really see on the stack now and what you think you'd have to do in the future. Like, how do you detect that Shores is running on this mass scale or Grover's is running on this mass scale?
So right now, there's definitely we're walking the fine line between like privacy concerns as well as with
Hmm.
overall capability delivery. We do not. We're prohibited, in fact, from monitoring specific, I would say, use patterns that are part of, for example, Amazon's Web Services contract, right? We can't introspect the privacy of what is actively being run. So part of that is the user agreements that end users are signing up for on the various providers. So we are subject to those kind of extending those agreements down through our hardware and software stack. And so I think it's an open question for the larger industry, actually, as to how, whether it's through the kind of open cloud APIs or whether it's through the direct access APIs with different type of licensing agreements that allow the types of, let's say, execution and use of the systems for specific intended purposes. I think that's still a lot of open area that the industry needs to address. And I think while we've been thinking and looking at software architecture, different layers of the stack, API modifications, that would come down the pipeline in the next, half decade, it's still very much an open question as to where the rubber meets the road and what the actual implementation details will look like or how the offering will change.
Yeah, because the circuits to do either of the algorithms, they're pretty unique. I mean, you could just see at a glance what's running, right? You could see the Fourier transformations in Shor's algorithm, and you could see that constant like narrowing that happens in Grover's, the bouncing back and forth to figure out yeah, it's just so visually stunning. Like you could just see nothing else is really running. So I would think that that could be detected at any level. I think that could be detected really right down at that last laser, electronic gate level. Like it should be detectable without technically violating privacy, but just knowing like, oh, we're doing this over and 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 over again for millions and millions of gates. So I do expect the language to change. The terms of agreement, service, whatever. I think that's going to have to reflect that at some point it's noticeable. And are you not allowed to do that? It'll be interesting. Like we'll be able to log in, right? There's stuff you can't do now, right? Like you can't run a bot farm on Amazon or GCP. They're going to stop you, right? It's against their serve. So are we? Do you predict that's going to happen? We're going to be like no Shores past this, no Grovers past that. Like is that going to have to be spelled out?
I expect the entire industry to start to rethink what this looks like, just as you said, like there's certain applications and licensing that you will agree to as part of
Hmm.
being able to use these services and capabilities. And whether they're publicly available or even privately available is still a big question, I think, as the machines become more and more and more powerful.
Yeah, and they're going to become weapons grade machines. I mean, in some way, like, are you already starting to rethink the whole physical security of these machines, like how portable they are or whatever? Because whenever I hear someone say, "Oh, we're going to shrink quantum computers down to a two Q wrap, whatever, two wrap," it's like I don't know if that's a great idea. I don't know how small you want them to be. How do you secure something like?
Physical security of the machines, data security, the information security aspects of the machines are very much top of mind.
Hmm.
And so everything from the IP that's located inside them to how they're being used, right? What is the overall kind of attack services of the software, the hardware APIs, right? If you follow IonQ, you're aware of some of the work that we've been doing and the different contracts that we have. Arliss, which was one of the contracts that we completed phase one last year on. Part of the aspects of that contract is focused on blind quantum computing. And a big part of that is the cybersecurity aspects of that and trying to apply some of the NIST standards for data security to quantum and understanding what this looks like. And through that lens of these kinds of exact use cases.
So I guess we could probably expect to hear more about IonQ beating the drum towards PQC for everyone, right? Like I would think it's going to be something you're going to be encouraging everyone to jump on, because I really don't think we have till 2035 anymore. I just don't, from what I'm seeing. But let's also celebrate the fact that look at all the great stuff we're going to do beforehand. You can't underestimate it.
Absolutely, right? I mean, the use cases that we have right now for drug discovery, for optimization, machine learning, AI, like the ability of, quantum to augment material science research and everything else, right? We just announced a paper was published on Archive not that long ago in terms of just advancing fundamental physics, right? In terms of, neutrinos with the, University of Washington and that. And so there's a tremendous amount of just new frontiers that, we expect, and that we have an entire applications team to, help participate and drive solutions for customers and work with researchers and really, open up, the possibility.
Do you have a couple of use cases that already your team has identified as, whoa, 2027, these are going to be instant home runs? Like, do you have any that are just the thing that they're dying to try once we hit that level of power for, let's say, 800 logical?
Well, I would pick chemistry as well as some of the optimization use cases. Those are two use cases that have already shown a lot of promise. We have examples on optimization from gate scheduling for airlines to optimization associated with the power grid, optimization associated with the how should I say this? The the packing, if you will, of, boxes in cargo systems, a
Like the
tremendous
knapsack
number.
problem? Yeah.
Knapsack-like
Yeah.
problems, yes, exactly, and so there's a number of optimization problems, constrained binary optimization problems fit extremely well to a quantum decomposition and solution on these machines, and then if you look at the breadth of chemistry problems in terms of simulating the orbitals and small molecules, that is a huge area of opportunity that we're very interested in. It doesn't even speak to some of these other, I would say, fundamental additions that are, I would say, unlocked or augmented through the use of quantum. That includes the work that we're doing, for example, with ANSYS, which at the end of the day, ANSYS is a computational aided engineering company where they're developing solvers and tools for, engineers to do crash modeling and, turbo machinery modeling and, or heart valve modeling, or whatever it is, right? But those graphs and finite element models that are generated as you try to solve them, at some point they result in a graph partitioning problem where you're trying to decompose the overall solution space onto different hardware. Well, that maps directly onto a quantum computer. And right now we've already demonstrated improvement there. That's at a, with current capabilities, a 12% improvement. You can only imagine what the improvement is going to be with going from like 36 qubits to 10,000 qubits.
Yeah.
So there's a huge number of applications that will continue to improve based off of what we've already seen, but I expect there to be whole new applications opening up that we haven't even thought about.
Yeah, I'm excited by anything done in the foundational aspect of physics too. I do believe there's a lot left to unlock. Some of that might come through AI, this idea that AI might analyze papers that are already done and find connections we never thought of before, just because there's so many of them out there. And some of that might come from then applying something to a quantum computer. There have been some sort of bogus headlines about like creating black holes and stuff like that, wormholes or whatever. But it's still exciting to think that maybe one day something will directly map to this true simulator of the universe, like Feynman said years ago, is the whole point of doing this work. So yeah, I did want to get into this more optimistic territory before we closed. And one thing earlier we were talking about blocking certain types of access because of security reasons. Now, on the flip side, as these machines are doing amazing things, you're going to have the opposite problem. A whole lot of people who want access. So, how many of these will there really be? And what kind of multiplexing will be in place so it won't be a bottleneck problem, right? Like let's say take something like fraud detection. Let's say you nail fraud detection and it's, orders of magnitude better than classical. If a bank can only access this one system once a month, it's not really that useful. So, like any thoughts to access?
Yeah, so there's a couple different aspects to that.
Hmm.
First, on the access side, we earlier this year, we put out a capability that allows round robin scheduling, if you will, from an access perspective. So it allows much more seamless overall usage of the hardware among multiple customers. So that at the end of the day, from an API perspective, it looks seamless in terms of using the APIs and executing shots across, various quantum circuits to be able to support multiple different workflows in kind of a hybrid environment, or even, reservations, for example, is another kind of use case model where you have a blocked amount of time. And so from an overall API perspective, we've been adding capabilities to the stack that allow these different interaction models with the systems that allow customers to really scale whatever they need to do. If they need dedicated time, they can get dedicated time. If they have the ability to take advantage of this interleaved type of execution, they can take advantage of that. That is kind of an access perspective. We've also been investing in just driving down the cost of our system. This is just through good plain engineering. Part of the work that we've been doing in our investments is looking at the subsystem costs, our cost modeling. What does this take to be able to drive these costs down so the unit economics continue to grow, so that by the time we're at these 2 million physical qubits and 80,000 logical qubits in 2030, we are investing in the component technologies that result in not just one system, but that literally we have the ability to create, hundreds of these systems to be able to put in our data centers, to be able to host these, so that you're not having a mass of users trying to access a single unique resource, but instead being able to start thinking about these quantum systems as a fleet of machines with failover, with redundancy, all of the expected illities you'd expect from kind of data center operations naturally. That's part of the investment we've been making for the last 4 years, 5 years, and we'll continue to just leverage as we move forward in time, right? That's all of our enterprise grade investments that result in driving usability to the end user in a way that allows them ideally unfettered access to these machines to be able to do the research, do the innovation, drive things forward. And so while unit economics from the side of the research isn't interesting, it's interesting from our perspective to be able to just drive enterprise grade availability and deliver that to customers so they can do the interesting work on their side.
Yeah, and if you have a lot of these machines, I would think in theory you can switch them on and off to become bigger or smaller as needed, right? Like you can do 8,000 logical if needed, or 4,000 and 4,000 if needed, or like, because not every circuit needs that many qubits, let's say.
It's interesting, yes. So one of the beauties of the current architecture that we have and the current connectivity and the way we've engineered the software stack, right? We have full control over the software stack from literally FPGA code that's running on system on a chip all the way up through our cloud integrations. So that full software stack we maintain, we own, we build. The quantum error correction layer, which sits, in kind of the middle of that stack eventually, is something that we can upgrade through time. And we can tailor it based off of need. And so you can envision a future where you have an ability as an end user to pick a class of hardware that allows you to be able to kind of tailor the the hardware instance to the kind of application and run that you need and make that active trade-off.
Yeah, to optimize all that, you'll probably need another quantum computer dedicated just to the front end, just to make sure everyone gets the best usage. That's pretty exciting. So before I let you go, IonQ was, of course, the first company to make real big waves when it came to the whole concept of investing in quantum and all that. I didn't know if you wanted to share any updates on how all that's going, on that whole journey. I know there was some news recently in the billion range, so I figured you might want to just touch on that.
Yeah, absolutely. So IonQ is really the best funded pure play public quantum computing company in the world, like full stop. And so we went public roughly 4 years ago. That gave us a bank account that allowed us to take things really from the lab into production and really double down on the engineering aspects, the R&D, everything we needed to do to drive the technology and our products forward. We've been continuing to invest as part of the recent transition of Peter Chapman to our executive chairman of the board and moving Niccolo from kind of an active board member, Niccolo Damasi, to our now CEO, has been a doubling down in terms of how we want to think about and position ourselves and the capabilities that we're trying to deliver to customers. And you see the acquisitions leveraging that, new thinking. You see the ATM that we had an at the market offering earlier this year driving that is driven towards trying to expand upon our overall kind of portfolio investment, including M&A activity. The recent, $1 billion, note that you mentioned is really about, supporting our commercial operations. It's a testament to the work that we've, put in place. It is a huge vote of confidence in the people and our roadmap and our technology. And we intend to use the overall investment work to really drive our operations forward. We have a lot of integration work in front of us. We have, big plans to continue driving IonQ as literally the 800-pound gorilla in the space, deliver unique capability and deliver novel, I would say, hardware and software that is just literally a generation to 5 generations ahead of everybody else.
Yeah, well said. I've got to say, when I look at that roadmap, it exceeds my wildest dreams. So none of this is investment advice, but that roadmap is just everything. I really hope it comes to pass exactly as shown. So with that, thanks so much for coming on, and good luck to taking us to that next level, and good luck with the challenges that will come with that next level.
Thank you so much, Konstantinos. It's been a great pleasure to talk to you guys today. And it was wonderful to be able to share a little bit about IonQ and kind of where we're headed, what we're doing, and everything else. So thank you.
That does it for this episode. Thanks to Dean Kassmann for joining to discuss IonQ. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on X and LinkedIn. Until next time, be kind and stay quantum curious.